Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 4.4, trigonometric functions of any angle. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. The objectives that we have for today will be to determine the principal and reference angles for any angle measured in both degrees and radians and sketch it in standard position. So this means that we are extending beyond quadrant 1, or the acute angles, and we are looking into quadrants 2, 3, and 4 as well. Furthermore, students will be able to evaluate all 6 trigonometric functions for any special angle, so those are the ones that we are memorizing the conversions between degrees and radians, without a calculator. So we will be able to do the evaluation of the 6 trig functions for angles without a calculator by using some tools. The tools are 2 special right triangles and how they are reflected through the x and y axes to produce different coordinates for x and y. In the first exercise, let's complete the table as quickly as we can, just to test our ability to convert quickly from degrees into radians for all of the special angles that we will take as the set of numbers that we need to be able to work with without a calculator. 0 degrees is 0 radians. 180 degrees is pi radians, and 360 degrees is 2 pi radians. 90 degrees is halfway between 0 and pi, so it's pi by 2, and 270 degrees is 3 pi by 2. Those are all of the quadrantal angles. Next, in green, I'm going to put all of the angles in radians that have a reference of 30 degrees. So 30 degrees is pi by 6, 150 degrees is 5 pi by 6, 210 degrees is 7 pi by 6, and 330 degrees is 11 pi by 6. Next I will take red, and I will write all the angles with a 45 degree reference angle. In quadrant 1, that's pi by 4. In quadrant 2, 3 pi by 4. In quadrant 3, 5 pi by 4. And in quadrant 4, 7 pi by 4. And lastly, we will look at all of the angles with a 60 degree reference. So in quadrant 1, 60 degrees is pi by 3. 120 degrees in quadrant 2 is 2 pi by 3. 240 degrees in quadrant 3 is 4 pi by 3. And 300 degrees in quadrant 4 is 5 pi by 3. Exercise 2 says complete the table below. The first example is done for us. So if the given angle is 7 pi by 3, we could sketch it by recognizing that we go 1 full revolution from 0 round to 2 pi, but 2 pi is equal to 6 pi by 3, and so 7 pi by 3 is an additional pi by 3 radians past 1 full revolution. So we are between the first and second rotations or revolutions. The principal angle then is the measurement from the terminal arm to the nearest x-axis. Rather, the principal angle is, if we backtrack 1 revolution, we would see that the principal angle is, let me write it here, 7 pi by 3 minus 1 revolution of 2 pi, which is 6 pi by 3, gives us a principal angle of pi by 3. Recall that the principal angle is contained from 0 radians inclusive up to but not including 2 pi radians. And the reference angle is the measurement from the terminal arm to the nearest x-axis, which happens to be the same as the principal angle in this case, because the principal angle lies in quadrant number 1. Now if we draw the sketch for negative pi by 3, we're going to go in the clockwise direction for a negative angle, an amount of pi by 3 radians, which is 60 degrees. And so the angle negative pi by 3 is here, and the angle lies in quadrant number 4. The number of rotations in the direction, it's in the first revolution or rotation. In the first rotation, and the direction is counterclockwise or anti-clockwise. The principal angle would be the angle that we get to land in that first revolution going in a counterclockwise direction, and so in red that angle is going to be 2 pi minus pi by 3, which is equal to 5 pi by 3. And the reference angle, which I will state up here, is the acute angle, which is between 0 radians and pi by 2 radians. It's the measurement between the terminal arm and the nearest x-axis, and it is always a positive angle because it lies between 0 and pi by 2. So the reference angle here is the difference between 0 and negative pi by 3, or the difference between 5 pi by 3 and 2 pi. Either way we look at it, the reference angle is again pi by 3. The next case, 11 pi by 3, sounds like it's going to be more than one revolution. So if we were to look at numbers of revolutions in terms of pi by 3, this is 0, this is 3 pi by 3. Coming back around, this is 6 pi by 3, or 2 pi. Coming back over here, we have 9 pi by 3. And winding around again, we have 12 pi by 3. So as we wind around, I'll use a different color, we go 6 pi by 3, 9 pi by 3, and 12 pi by 3 would take us all the way to the starting or initial arm again. So we want to go 11 pi by 3, which is going to be in here. So basically we're taking half of a circle, so the bottom half of the circle, or the bottom half of a revolution, looks like this. And if we cut that into thirds, we would have 1, 2, 3 pi by 3s. So that's why I'm landing here. Okay, so that takes me with the green arrow and the spirals to 11 pi by 3, and it's one full rotation, not quite the second. So it's between the first and second rotations. First and second rotations, and it's in the counterclockwise direction. So the principal angle I would have to unwrap or subtract from 11 pi by 3. I would have to subtract 2 pi, which is 6 pi by 3, and 11 pi by 3 minus 6 pi by 3 is 5 pi by 3, which does indeed lie between 0 and 2 pi. And then to get the reference angle, I measure from the nearest x-axis to the terminal arm, and I need an acute angle between 0 and pi by 2. That again is pi by 3. And of course the quadrant we see is quadrant 4. The angle negative 8 pi by 3, well, 1 pi by 3 is a sixth of a circle. So I want to go 8/6 of a circle in the clockwise or negative direction. So if I go 1, 2, 3 sixths of a circle, each sixth of a circle is equal to pi by 3 radians. And the reason we know that is because one circle, or one revolution of a circle, is equal to 2 pi radians. And if I divide by 6, 2 pi over 6 reduces to pi over 3, and dividing 1 by 6 gives me 1/6 of a circle. So 1/6 of a circle is 60 degrees, or pi by 3 radians. So if I went 1, 2, 3, 4, 5, 6 sixths, 7, 8/6 of a circle, I land in quadrant number 3. And of course my starting point is always at 0 degrees or 0 radians, which is the initial arm, which lies on the positive side of the x-axis. Okay, and then we notice that the angle is between the first and second rotations in the clockwise direction. And to get the principal angle, I would have to take my negative angle and add one revolution plus another revolution and another revolution enough times until the angle lies between 0 and 2 pi. So if I add 2 pi, which is the same as 6 pi by 3, to the original angle of negative 8 pi by 3, I would get negative 2 pi by 3, which is still negative, which means that I have to add 2 revolutions before I get a positive angle. The positive angle that I will be getting will be the angle in red. And so we will have negative 8 pi by 3 plus 2 pi plus another 2 pi. So we could have just added 4 pi in one go. So 4 pi is equal to how many pi by 3's? 4 pi over 1 is 12 pi by 3. And so negative 8 pi by 3 plus 12 pi by 3 is 4 pi by 3. And that makes sense because we can see we are going to get a reference angle of pi by 3 radians, or 60 degrees, into quadrant 4. And so that principal angle is 4 pi by 3. And the reference angle we just said is pi by 3, measured from here, the nearest x-axis, to the terminal arm. All right. Exercise 2, let's review once more. Draw the two special triangles measuring the angles in radians. So I'm going to draw the scalene triangle with an angle of 30 degrees, or pi by 6 radians down below, and pi by 3 radians up at the top angle. And the hypotenuse will be 2k. The height of the triangle will be 1k, or just k, and the base of the triangle is the square root of 3 times k. The isosceles triangle has two acute angles of pi by 4. I'm going to use the same measurement for the hypotenuse to keep it simple. Sometimes people use 1 or 1k for the hypotenuse of the isosceles triangle, and that is fine. But then my height and base will both be the square root of 2 times k. So we're going to use these two triangles, which contain acute angles. Remember, acute angles, like reference angles, are contained from 0 radians to pi by 2 radians. So here I have my three special acute angles that I can measure from the triangles, and we will use it to fill in a table for all of the 6 trig functions. Now the trig functions have been grouped as reciprocal pairs. And what I mean here is that the sine theta ratio is the opposite over hypotenuse, and the cosecant ratio is the reciprocal of opposite over hypotenuse, which is hypotenuse over opposite. And so just to kind of take stock of where we are, in the beginning of the chapter, 4.1 to 4.3, we were looking at a lot of definitions, so we were very verbally focused on trigonometry. Now we are starting to branch into the numerical aspect of trigonometry. And so without a calculator, if the angle is pi by 6 radians, the opposite over the hypotenuse ratio is 1k over 2k, or 1/2. The cosecant then is 2 over 1, or 2. For pi by 4, the opposite over hypotenuse is the square root of 2 over 2, and the reciprocal of that is 2 over the square root of 2, which reduces. A number divided by its square root is the square root again. And the angle of pi by 3 has a sine ratio of opposite over hypotenuse, square root of 3 divided by 2. The reciprocal is 2 divided by square root 3. Sometimes people rationalize this by multiplying the top and the bottom of the fraction by 1 in the form of square root 3 over square root 3. I am comfortable with leaving 2 over square root 3 as the answer, as long as if it's practical or convenient that we know we could rewrite in the rationalized denominator form. All right, now let's go through and work out the cosecant ratio, rather the cosine ratio and its reciprocal secant ratio. One thing to keep in mind is that reciprocal is not the same thing as inverse and is not the same thing as opposite. Let's get in the habit of using the correct words. Reciprocal means to raise a fraction or a base to a -1 exponent, or to flip the fraction. So the cosine ratio is adjacent over hypotenuse. So if we take a ratio of the adjacent sides to the given angle of pi by 6 over the hypotenuse, we get the square root of 3 over 2, and the reciprocal is 2 over square root 3. So we get the same ratios that we had for the sine of pi by 3. And then the cosine of pi by 4 is, if we use this pi by 4, the adjacent is square root 2 times k over the hypotenuse of 2 times k. It gives us root 2 over 2, and the reciprocal is square root 2. The last ratio is 1/2 for the cosine of pi by 3, and the secant of pi by 3 is 2. The tangent ratio is opposite over adjacent, and its reciprocal function is the cotangent function, whose ratio is adjacent side over opposite. So the tangent of the angle pi by 6 is opposite over adjacent, which is 1 over square root 3, which can be rationalized to give us square root 3 over 3. This one is easy to reciprocate though, and the reciprocal is square root 3 for the cotangent of pi by 6. The cotangent of pi by 4, rather the tangent of pi by 4, is opposite over adjacent, and so opposite over adjacent gives us square root 2 over square root 2, which is equal to 1. This is because the opposite and the adjacent sides are equal lengths in the isosceles triangle. The reciprocal of 1 is 1, because swapping the opposite and the adjacents when they are the same looks the same as without swapping the sides. And the tangent of pi by 3 is opposite from pi by 3 over the adjacent, which is square root 3 over 1, or simply square root 3, and the reciprocal for cotangent of pi by 3 is 1 over square root 3. Like everything else, with exposure and practice, we will be very familiar with these to the point that it is like we have memorized these values. Okay, we've just been looking at the special non-quadrantal angles of 30 degrees, 45 degrees, and 60 degrees, and their trig ratios, or the trig function values. Now we are going to place those 30, 45, and 60 degree reference angles in all 4 quadrants. So we can take acute right triangles drawn in any quadrant, and then we can reflect them into the other quadrants. Let's consider the terminal arm that connects the first quadrant point here at 1 comma square root 3. Square root 3 is approximately 1 point something, because the square root of 3 lies between the square root of 1, which is 1, and the square root of 4, which is 2. So this is 1 comma 1 point something. And we are going to make a right triangle to the x-axis, because we always will measure our reference angles to the x-axis. So let's call that angle theta. So we know that the x-coordinate is 1, the y-coordinate is square root 3, and that can label 2 sides of the triangle. And we can use Pythagorean theorem to come up with the hypotenuse. So 1 squared plus the square root of 3 squared is equal to the hypotenuse squared. So 1 plus 3 is 4. If 4 is the hypotenuse squared, the hypotenuse is 2. Okay, so the reference triangle that we get from this terminal arm is a right triangle, and we have the triangle labeled here. The hypotenuse is the radius of the circle that is formed if you take that terminal arm and you rotate it around from the center point at 0, 0. So this is a point that we could label x comma y. And so the adjacent is x, the opposite is y, and the hypotenuse is r for the radius of the circle. Let me just move my x a little bit lower here. So the center is at 0, 0. This is x, and this is the theta reference in here. I don't have enough room to draw theta reference inside there, so I'm just going to put it outside. Okay, so when we solve for the hypotenuse using Pythagorean theorem, we have to take a square root. That gives us a plus or a minus, but since hypotenuse is a distance or a radius, it cannot be negative, so we choose only the positive root. Alright, so now let's use this information and complete exercise 5. We're going to take that same point, 1 comma square root 3, which has positive x and positive y coordinates and therefore lies in quadrant 1. And then we're going to take that point and reflect it either through the y-axis or the x-axis to get a point that lies in quadrants 2, 3, and 4, and then we'll complete the table. Okay, so the first thing we want to do is to sketch a reference triangle. So I'm going to do that here. It's the same triangle we just had with an x-coordinate of 1, a y-coordinate of square root 3, and a hypotenuse of 2. Our reference angle is 60 degrees, or pi by 3 radians, and the actual principal angle in quadrant 1 is going to be pi by 3. We can see this because if we measure from the nearest x-axis, The nearest x-axis is at 0 radians, and we're going in a counterclockwise direction, so we add. So the principal angle is pi by 3. The reference angle is the size of the angle between the terminal arm and the nearest x-axis, but the reference angle is always the same as the quadrant 1 principal angle. So again, we get pi by 3. The sine of this angle, we had just seen this by looking at the reference triangles or the acute triangles. The scalene triangle gives us, it doesn't look very scalene, I think I'll redraw it. So pi by 3 has an opposite of root 3k, an adjacent of root of 1k, and a hypotenuse of 2k. So the sine of pi by 3 is root 3k over 2k, which is square root of 3 over 2. The cosine is 1/2, and the tangent is square root 3. We saw that earlier in exercise 4. Now, if we take that point and reflect it into quadrant 2, then it comes directly across. The y-coordinate is the same, but the x-coordinate has changed sign. So now this point has an x-coordinate of -1, a y-coordinate of root 3, and a hypotenuse of 2. The reference angle is still inside the triangle here of pi by 3, but the principal angle is now different. In the principal angle, if we go all the way to pi and backtrack the reference angle, we get a principal angle of pi minus, or clockwise, pi by 3, which is 2 pi by 3, or 120 degrees. From here, we see that the sine of the angle, which is based on the opposite over the hypotenuse, the opposite is still an opposite y-coordinate, or distance of square root 3 over 2, so that doesn't change. But now the cosine of the angle, because we're going to the left and the x-coordinate has changed sign upon reflecting through the y-axis. Again, the y-axis has an equation of x equal to 0, so going from right to left, we're going through x equals 0. So the x-coordinate, or the adjacent, is -1 divided by 2, and the cosine of a quadrant 2 angle is negative. The tangent is the opposite over adjacent, but in this case the opposite is the square root of 3 y-coordinate, and the adjacent is -1. So we get square root of 3 over -1, which is equal to negative square root 3. So by changing the quadrant, we are changing distances into x and y coordinates, which may be positive or negative depending on which quadrant, 1 or 2 or 3 or 4, that the terminal arm and therefore the angle lies in. So if we take that again and repeat, we can reflect the point from quadrant 2 down into quadrant 3. And we see in this case our reference triangle has an x-coordinate of -1, a y-coordinate of negative square root 3, and a hypotenuse still of 2. We have the same reference angle of pi by 3, but in this case our principal angle is going to be pi plus pi by 3. And we will still have the same reference angle in quadrant 4. I'll write that down now. Pi plus pi by 3 is 3 pi by 3 plus 1 pi by 3, which is 4 pi by 3. And now if we take a look at the sine, which is the opposite over hypotenuse, in this case the opposite distance from this angle is really a y-coordinate, which is negative. So while distances are positive, coordinates or positions can be positive or negative or 0. So we have an opposite coordinate of negative root 3 over the positive hypotenuse or radius, which is always a positive radius or hypotenuse, of 2. And so we get negative square root 3 divided by 2 for the sine of the angle. The cosine of the angle is the adjacent over hypotenuse, and the adjacent distance to this central angle, well, it's not really a distance, it's a coordinate of -1 over the hypotenuse of 2. And the opposite over hypotenuse, the opposite over adjacent for tangent will be negative square root 3 divided by -1, which is positive square root 3. And lastly, in quadrant 4, if we take our point and reflect it, our reference angle still, as we said, has the reference angle of pi by 3. But now to get the principal angle, we go all the way to 2 pi and backtrack the reference angle of pi by 3, giving us 5 pi by 3, which is 300 degrees. The sine of 300 degrees, or the sine of 5 pi by 3, well, we look at the coordinates. We have a positive x coordinate, because we're in quadrant 4, but a negative y coordinate, and a positive hypotenuse or radius of the circle of 2. So sine of 5 pi by 3 is opposite over hypotenuse. The opposite is negative root 3 because the y coordinate is going down, or the y coordinate is negative. So we get negative square root 3 divided by the positive hypotenuse or radius of the circle of 2. The cosine of 5 pi by 3 is the adjacent, so adjacent to this red central angle is 1, and it's a positive 1 divided by the hypotenuse of 2. And the tangent of pi by 3 is the opposite, negative root 3 divided by positive 1 gives us negative root 3. So this patterning and this reflecting and changing the signs of x and y, depending on which quadrant we are in, has adjusted the signs, pluses and minuses, of sine theta, cosine theta, and tangent theta, compared to when we did it for only quadrant 1 or acute-sized angles. So let's generalize this information. To summarize exercise 5, we can see that the 6 trig functions or ratios can be evaluated for any non-quadrantal angle. So the non-quadrantal angles, recall, are the angles in a quadrant, not on an axis. And we can see, oh, I wrote that there, that since r squared equals x squared plus y squared for a circle, if we have a point xy here, this is going back to the first week of Math 150, where we talked about the radius of a circle being related to the x and the y coordinates of a point by Pythagorean theorem. Then we know that radius is the positive root of x squared plus y squared to get a positive distance, and we can rotate the radius all the way around the circle to get the same triangle in different quadrants. When we do that, we have all 4 principal angles with landing in different quadrants. As a result, the dimensions or the sides of the triangles and the proportions of the sides opposite, adjacent, and hypotenuse do not change. What does change, however, is whether the opposite coordinates, the adjacent coordinates, will be positive or negative, depending on whether x and y in quadrant 1, 2, 3, and 4 are positive or negative. For example, in quadrant 1, x is positive and y is positive. In quadrant 2, x is negative, but y is still positive. In quadrant 3, x is negative and y is negative. And in quadrant 4, all x coordinates are positive and the y coordinates are negative. So instead of calling the sine of the angle the opposite over hypotenuse, we can be more general and extend beyond triangles and not deal with an opposite and a hypotenuse and an adjacent, but we can refer to this as a point x comma y, and so the opposite gets generalized by calling it y, the adjacent gets generalized by calling it x, and the hypotenuse gets generalized by calling it r for radius. And that's what we saw from the equation of the circle. X, y, and r for the central angle inside here of theta. So as a result, the sine of the angle is now more generally referred to y over r. The cosine, and so its reciprocal cosecant is r over y. So these are reciprocal pairs. Cosine of the angle was adjacent over hypotenuse. It's now x over r for radius. The secant of the angle is the reciprocal r over x. and the tangent of the angle was opposite over adjacent. It is now y over x, and its reciprocal cotangent of an angle is x over y. So I'm just going to write again in here that these are reciprocal pairs. So these are the definitions that we want to use from now on, as they are more general because they allow us to deal with an angle theta, not just that lies inside a triangle and has ratio values including the opposite, adjacent, and hypotenuse, but we can use theta in any quadrant where we are not really making triangles, but we are making related reference triangles in quadrants 1, 2, 3, 4 by reflecting the reference triangle of quadrant 1 into any of the other 3 quadrants. As a result, we have to deal with positions or coordinates as opposed to positive distances for the opposite and the adjacent. So y is the generalized opposite and x is the generalized adjacent. All right, with this in mind then, let's try a couple of examples. Evaluate the following trig functions without a calculator. Identify the quadrant in which the angle lies and the angle's reference angle. When we have sine of 45 degrees, 135, 225, and 315, we know that the reference angle is 45 degrees. I will use degrees when degrees are stated in the problem. 45 degrees lies in quadrant 1, 135 degrees lies in quadrant 2, 225 degrees lies in quadrant 3, and 315 degrees lies in quadrant 4. What I'm going to do is draw my isosceles triangle here and put 45 degrees down here. And I need for sine the opposite, which is root 2k, over the hypotenuse of 2k. But what I also need to know is if I put that triangle into each of the different quadrants, what will the y-coordinate over the radius be? Well, the radius is always going to be positive, but the y-coordinate for quadrant 1, we said, is positive. So for my quadrant 1, I will take a positive 2k over 2k, rather a positive square root 2k over 2k, and I get positive root 2 over 2. So just to see our quadrant 1 triangle, we can confirm that the y-coordinate is positive and the hypotenuse is positive. Now to take that triangle and reflect it into quadrant 2, we're keeping the same size triangle, so the base, the height, and the hypotenuse are the same. So the ratios will be the same, but potentially we could have a different positive or negative sign. But in quadrant 2, the y-coordinate is still positive. So the sine of the angle, which by definition is y over r, is going to be positive square root 2 over 2. Now in quadrant 3, the y-coordinate is now negative. So for y over r, we will have a negative square root 2 divided by a positive hypotenuse of 2. So the same ratios, but different positive or negative depending on the quadrant. And lastly, in quadrant 4, this triangle reflected down, we're the same sides of root 2k, and hypotenuse 2k, and the y-coordinate is negative for going down into quadrant 4, and the radius is positive. So we still get square root of 2 over 2, but a negative overall. In the second case, the cosine of 30 degrees, 150, 210, and 330, these are all principal angles with a reference of 30 degrees. Since I'm given degrees in the problem, I'm using degrees in the answer. We have quadrant 1, 2, 3, 4, again in order. So our reference triangle, if we draw it in the plane already, a reference triangle has a 30-degree angle. And we see in quadrant 1, we have the cosine of the angle is now x over r, generalized from the adjacent over hypotenuse. And just to complete this, the sine of the angle used to be considered as opposite over hypotenuse, but we are generalizing it to the y-coordinate over the radius r. If this is a triangle whose point is in a circle, for example. Okay, so the cosine of 30 degrees, we have the 30-degree central angle. The reference angle is measured from the x-axis, not measured from the y-axis. And we have the triangle has an opposite of 1, an adjacent of root 3, and a hypotenuse of 2, or 1k, square root of 3k, and a hypotenuse of 2k. So we're not interested in the opposite or the y-coordinate, we're interested in the x and the radius. So we have that the cosine of 30 degrees is a positive root 3 divided by 2. Taking that point and reflecting it into quadrant 2, we end up getting this triangle with an x-coordinate that is negative root 3 and a radius of 2, so we get negative root 3 over 2. In quadrant 3, if I drew my circle a bit better, it's not very accurate for the circle. In quadrant 3, we see that the x-coordinate is still negative, and the y-coordinate is, the hypotenuse is still positive, and we get negative square root 3 over 2. And in quadrant 4, we see that the x-coordinate is the positive root 3 from before, lying along here, and the hypotenuse or radius is 2, giving us positive square root 3 over 2. Lastly, we will repeat the process for the 60-degree reference angle, and the principal angles in quadrant 1 are 60 degrees, in quadrant 2 is 120 degrees, in quadrant 3 is 240 degrees, and the principal angle in quadrant 4 with a reference of 60 is 300 degrees. So this picture looks like this. Our central angle is 60 degrees. Maybe I won't make this triangle so steep. So 60 degrees is inside here. And we are looking for the tangent of the angle, which we used to call opposite over hypotenuse when we were only dealing with right triangles. But now we are looking for non-acute angle trig function values. So we are going to replace opposite with y and adjacent with x, so that we can go from positive distances to positive, negative, or 0 coordinates. So the opposite for this triangle is a y value, and we get root 3, and the adjacent or x value or coordinate is 1. And so for tangent of 60, we have y over x, which is positive square root 3. In quadrant 2, if we reflect the triangle, we get a negative 1 for x and a positive root 3 for y. So y over x is positive root 3 over negative 1 is negative root 3. In quadrant 3, we still have a negative 1 for x, but now we have a negative root 3 for y. So y over x is negative root 3 over negative 1, which is positive square root 3. And in quadrant 4, we have our positive 1 for x, and going down into quadrant 4 gives us a y-coordinate of negative root 3. So y over x is negative square root 3. Okay, so we're going to fill in some blanks, and we are going to see for non-quadrantal angles, angles that lie in the quadrants, both x and y are, well, if the angle is inside the quadrant, then neither x nor y could be positive. So we would, neither x nor y could be 0, so we say that x and y are non-zero, either positive or negative, but not 0. For quadrantal angles, angles that lie on a quadrant, either x or y is 0, but not both, because if x and y were 0, we would be talking about the origin. So for a quadrantal angle, either the x-coordinate or the y-coordinate is 0. For quadrantal angles on the y-axis, the value of x is 0, because this is the line x equal to 0. And for quadrantal angles on the x-axis, the value of y is equal to 0, because the equation of the x-axis is y equals 0. And as we know, a non-zero number divided by 0 is said to be undefined. So now we are connecting some verbal with some numerical, and of course we know that we will be leading to graphical and eventually algebraic. So let's evaluate the trig functions for quadrantal angles, or the angles that are on the axes. If we were to plot these quadrantal angles, we have 0, we have pi by 2, we have pi, and we have 3 pi by 2. Those are the four principal quadrantal angles. 2 pi is not a principal angle because it's already on a terminal arm where a principal angle is already designated. So I'm just going to write not a principal angle. And let's recall that principal means first or one, and the principal angles are simply containing 0 up to but not including 2 pi. So it allows us to sweep one full revolution but not repeat any terminal arm. So let's use our definitions of sine of the angle, which is y over r, cosine of the angle, which is x over r, tangent of the angle, which is y over x, and let's use their reciprocals to fill in the table for the quadrantal angles, and I will repeat again for 2 pi, even though it's not a principal. Well, in order to do this, we want to label some coordinates here. At this point here on the unit circle, which is a circle of radius 1, we have 1, 0. At pi by 2, this is a point with x and y coordinates 0, 1. The x, y at the angle of pi is negative 1, 0. And the x, y coordinates at the 3 pi by 2 terminal arm is 0, negative 1. And of course, this is a circle of radius 1, so r is equal to 1 at every point on the circle. So when theta is equal to 0, we focus on this point here, and the y coordinate is 0 divided by a radius of 1 is 0 over 1, which is 0. At pi by 2, the y coordinate of 1 divided by the radius of 1 is 1 over 1, which is 1. At the angle of pi, the y coordinate of 0 divided by the radius of 1 gives us the sine of pi, or the sine of 180 degrees, to be 0. At 3 pi by 2, the y coordinate of negative 1 divided by the radius of 1 says that the sine of 3 pi by 2, or 270 degrees, is negative 1. And 2 pi is a repeat of the position at theta equal to 0, so we know that the sine of 2 pi is going to be a repeat of the sine of 0. Then the reciprocal for the cosecant, the reciprocal of 0 is undefined because it is 1 over 0. Non-zero over 0. The reciprocal of 1 is 1, the reciprocal of 0 is undefined, the reciprocal of negative 1 is negative 1, and the reciprocal of 0 is undefined. Let's repeat the process now, focusing on the x-coordinate over the radius in order to calculate the cosine of the angle. So starting at the angle of theta equal to 0, the x-coordinate of 1 divided by the radius of 1 says 1 over 1 equals 1, and the reciprocal of that is 1. At pi by 2, the x-coordinate of 0 divided by the radius of 1 gives us 0, and the reciprocal of 0 is undefined. At theta equals pi, the x-coordinate of negative 1 divided by the radius of 1 is equal to negative 1, and that reciprocal is negative 1. What that says then is that the secant of pi radians is equal to negative 1. And from now on, we're going to need to know that, or we're going to need to draw a picture and very quickly come up with it. At the angle 3 pi by 2, the x-coordinate of 0 divided by the radius gives us that the cosine of 3 pi by 2 is equal to 0. The secant of 3 pi by 2 is undefined. At 2 pi, the cosecant of the angle 2 pi is a repeat of the cosecant of 0 because the x-coordinate is a repeat of the x-coordinate at the angle 0. So 1 over 1 is 1, and the reciprocal is 1. Let's do the last one for tangent. You might want to try pausing the video, doing it on your own, and checking with me. All right, at the angle 0, the y-coordinate is 0, the x-coordinate is 1, so y over x is 0, and the reciprocal of 0 is undefined. In other words, 1 over 0 would be the x over the y-coordinate. At pi by 2, y divided by x is 1 divided by 0, which is undefined, and the reciprocal of undefined would be 0 over 1, which is 0. At theta equal to pi, y over x is 0 over negative 1, which is 0, whose reciprocal is negative 1 over 0, which of course is undefined. At 3 pi by 2, y over x is negative 1 over 0, which is undefined, and the reciprocal of undefined is 0. And lastly, at theta equal to 2 pi, we have the coordinates 1, 0 repeated, And so we get the same ratio values that we had in the first column. 0 for tangent of 2 pi, and the cotangent of 2 pi is undefined. Well, we now know how to fill in this big table with all of the special angles, the principal special angles, some quadrantal angles and some non-quadrantal angles. I am going to use a highlighter here to identify the quadrantal angles, and then I will use a highlighter to identify the quadrantal angles in the table. I recommend that you use different colored highlighters and do as I do. To come up with the quadrantal angle trig ratios, we simply need to know the ordered pairs at these 4 points on the unit circle. The unit circle is a circle of radius 1, so this is the point 1, 0, 0, 1, negative 1, 0, and 0, negative 1, corresponding with the principal angles of 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Background, of course, would take us to 360 degrees. And we've just filled these in. The first column or row across is asking us to write the angle in radians. I'll leave that to you to do as an exercise, just to practice your degree to radian conversion very quickly. I'm not going to fill in the entire table with you, but I will show you how to get started. Let's maybe pick the sine and the cosecant ratios. I don't have the reciprocal pairs one after the other, so you may want to do them in the same color as you go across. So the sine of 0 degrees, well, let's just recall our basic definitions. Sine of theta is y over r. Cosine of theta is x over r. And tangent of theta is y over x. So from the ordered pairs, we have the radius is always 1 on the unit circle. And we can see that sine of 0 is y over r, 0 over 1 is 0. And the reciprocal of that is undefined. For 90 degrees, we go to the point here. At 90 degrees, the y-coordinate is 1, divided by the radius of 1 is 1. The reciprocal of that is 1. For 180 degrees, the y-coordinate of 0 divided by 1 is 0, and the reciprocal is undefined. For 270 degrees, the y-coordinate of negative 1 divided by the radius is negative 1, and the reciprocal of that is negative 1. And this is the beginning of the second revolution, or the second rotation of the terminal arm, second rotation, and so we have a repeat of the values, 0 and undefined. Okay, we can take a look at maybe filling in for cosine now, and its reciprocal secant, for all of the angles that have a reference of 30 degrees. So the reference of 30 degrees, we can see here in green already. And we can use the green highlighter to highlight all of those principal angles with a 30-degree reference angle. So not much is going to change throughout here, because we have the same size triangle in each quadrant. The only difference is whether the x-coordinates are positive or negative for the cosine. So in quadrant 1, x is positive. In quadrant 2, x is negative. In quadrant 3, x is negative. And in quadrant 4, x is positive. So that means cosine is positive in quadrants 1 and 4, but the cosine of a quadrant 2 or 3 angle will be negative. But apart from that, we just need to use the 30-degree reference triangle. So the 30-degree reference triangle could be drawn like this. Here is my central angle measured from horizontal. The opposite is 1k, the adjacent is square root 3k, and the hypotenuse is 2k. So the cosine of 30 degrees is root 3 over 2. And that will be the same positive ratio. Maybe I'll put that in black just so it stands out a little bit. Square root 3 over 2. In quadrant 1 and quadrant 4 will be positive, because the x is positive in quadrant 1 and quadrant 4. And cosine is x over r. r, of course, is always positive because it is a radius or a distance. The reciprocal of those values is 2 over square root 3. Now, to come up with 150 degrees and 210 degrees for cosine, or rather the cosine of those angles, we know that we've got the same ratios, the same size triangles. There's our reference angle. But now the x-coordinates in quadrant 2 and 3 are negative. So the only difference is that this ratio will be negative root 3 over 2. Okay, let's just do the same thing for the sine of 30 degrees. In the sine case, we have y over r, and in quadrant 1, y is positive. In quadrant 4, however, y is negative. In quadrant 2, x is negative and y is positive. And in quadrant 3, x is negative and y is negative. So when we are looking at the sine coordinates, wherever y is positive, the sine of the angle will be positive. Y is positive in quadrants 1 and 2, so sine is positive in quadrants 1 and 2. And so in fact we can go all through quadrant 1 and all through quadrant 2 for sine and put positive. Then in quadrant 3 and quadrant 4 we can put negatives for sine. Similarly, cosine is positive wherever x is positive. X is positive to the right of the y-axis, meaning in quadrants 1 or 4. So for cosine, we can put positives all the way through quadrant 1 and positives all the way through quadrant 4. And x is negative in quadrants 2 or 3, so cosine will be negative in quadrant 2. See, already negative, 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 negative for quadrant 3. And then we just need to figure out what the reference angle is for 30 degrees. Well, the reference angle, rather, is 30 degrees, so what's the sine ratio? Opposite over hypotenuse, or y over x, will be 1 over 2. So this will be positive 1/2, positive 1/2, negative 1/2, and negative 1/2. I will leave you to fill the rest of this in, but I would encourage you to use highlighters and colors so that you can see the patterns. For example, the 60-degree triangle has a turquoise, on one of the grids I've given you, has a turquoise line, and so we can use the turquoise highlighter for all of the 60-degree reference angles. And we have purple for the 45-degree angle, 45-degree reference angles, meaning 45 degrees, 135 degrees, 225 degrees, and 315 degrees. And so I'm going to highlight that in purple. And so we see that we have the quadrantal angles in yellow and the non-quadrantal angles, the angles that lie in the quadrants, in either green, purple, or turquoise. We would also want to draw the remaining reference triangles. I'm going to draw a purple reference triangle for the isosceles with my central angle of 45 degrees here and my hypotenuse and my two legs. And I'm going to use turquoise. I don't have turquoise pen, so I'll use blue for my 60-degree reference angle. And my reference angle is measured from the horizontal. So we have root 3k, 2k, and k. This should be enough information, along with the correct signs, positive or negative, to complete the table. To summarize the signs then, we see in quadrant 1, x and y are positive, which means all of the trig ratios will be positive. So I'm going to use an A in quadrant 1 to indicate that all trig functions will be positive. In quadrant 2, y is positive, which means that the sine ratio is positive, but x is negative, which means the cosine ratio is negative. Tangent, which is y over x, will be positive divided by negative, which is negative. As a result of the three primary trig functions, only sine is positive. Of course, that means its reciprocal will not change sine, so the reciprocal is also positive. I'm going to write an S in quadrant 2 to indicate that sine, the sine function of a quadrant 2 angle, and its reciprocal are positive for angles coming out of quadrant 2. For angles in quadrant 3, we see that the x-coordinate is negative and the y-coordinate is negative, which means that the sine ratio of a quadrant 3 angle is negative, cosine of a quadrant 3 angle is negative, but tangent will be negative over negative or positive. So tangent and its reciprocal cotangent will be positive for angles in quadrant 3. And so I will indicate this by putting a T in quadrant 3, telling me that the tangent ratio is positive, and so is its reciprocal. In quadrant 4, we see that x is positive, and therefore the cosine ratio will be positive. But y is negative, which means that the sine ratio and the quotient of y over x, or tangent, will also be negative. So the principal ratio, or the primary ratio, to be positive in quadrant 4 is the cosine. And so too will its reciprocal of secant. So this memory aid will help you to remember which primary trig function is positive in each quadrant. Here we have another organizer of different information. We can see that if we are on the unit circle and r is equal to 1, then sine of an angle is not just y over r, but it's y over 1, and so the y-coordinate of a point on the unit circle is the sine of the angle of that terminal arm. We'll come back and fill this in class, as I think we've got a lot of information for now. But the other organizer that I want to show you is with these highlighted colors again, and we will talk about different names for these angles as we go around and around and around looking at coterminal angles. We'll save this also for class. So that concludes 4.4, trig functions of any angles. It really is a numerical summary of how to calculate sine, cosine, tangent, and the reciprocal functions for all of the special angles in quadrants 1, 2, 3, and 4. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.